Nice. All right, so 6.5 is on the energy of phase changes. We are going to calculate the amount of energy required for any substance, different substances, to undergo phase changes. Okay, meaning, again, solid to liquid, liquid to gas, or vice versa, gas to liquid, liquid to solid. Or if we're feeling extra fancy, sublimation, solid to gas, or deposition, gas to solid. I don't think I'll do that more than like once. But either way, we're going to calculate the energy involved in substances changing phase. Whole bunch of words. Does adding heat always make a substance hotter? If I add thermal energy, aka heat, to a substance, does it always increase the temperature of that substance?
Yes. Yeah. No.
Now, what's it feel like the answer should be? Feels like the answer should be yes, which means it's probably what? No. Okay, the answer is no. Okay, otherwise I wouldn't have asked the question, right? That's kind of one of those, like, it feels too obvious. It's got to be the opposite of what you think it is. The answer is no. Now, that feels kind of strange, but let me explain. During a phase change, okay, if you are going from solid ice, solid water, to liquid water, and it's melting, while that change is taking place, the temperature is constant. That sounds very strange. But if you have ice water, that is at 0 degrees Celsius. Assuming that it's been there long enough so that it can reach thermal equilibrium, right? If I have a mixture of ice and I have a mixture of water, it's 0 degrees Celsius. Always. Now, if there is no ice left, right? The ice is fully melted and the phase change is done and complete, and now I just have a glass of water, the temperature can now change. The temperature of pure substances, meaning like pure solid phase, pure liquid phase, pure gas phase, can change when heat is either added or removed. But during a phase change, you add more energy, but the energy doesn't change the temperature. Okay, sounds very weird. But let's talk about that. So sometimes a substance that is being heated remains at the same time. In this situation, the energy added is being used to overcome intermolecular forces of attraction between the molecules. Water molecules are attracted to other water molecules by blank. What's the intermolecular force that holds water molecules together?
Hydrogen bonds.
Yep. Okay, hydrogen bonds. It's been a while on that stuff, but yes, hydrogen bonding. At room temperature, water is a liquid. If enough energy is added to water, the kinetic energy of the molecules can become greater than the intermolecular forces of attraction, and the water will become a gas. That's boiling, or evaporation in small percentages, right? So phase changes occur, and we did talk about this in the intermolecular forces unit, unit 3. Phase changes occur when you've added enough energy to increase the kinetic energy, the energy of motion, to the point where that is a larger quantity than the attractive force holding it together, right? My liquid, which is like this, free-flowing, but attractive forces between the molecules. If I speed those molecules up faster and faster and faster and faster, eventually they're moving with greater energy than the attractive force holding them together, meaning they can fully separate from one another and turn into a gas. Make sense? So note the 2 plateaus on the graph below. It's on my next slide. It's below on your page. Okay. These represent the blank point and the blank point. Take a look at those temperatures. What do those 2 plateaus represent? Melting point and boiling point. If I'm going the other direction, what are they called? Because melting and boiling means I'm going from like colder to hotter, right? If I'm going from hotter to colder, what are they called? Freezing point. We're missing the other one. If I go from gas to liquid, what's that called? Condensing point, yes. So I'm going to call these the freezing slash melting point, okay, and the boiling slash condensing point, okay? Because it just depends on the direction, right? But freezing and melting occur at the same time. It's just a matter of what I've started with and what I'm turning it into, right? If I start with liquid, turn it into solid, that's freezing, and it happens at 0 degrees Celsius for water. If I started with solid and I'm going to liquid, that's melting, and it happens at 0 degrees Celsius. So that point, that temperature is the same. It's just a matter of whether we're getting hotter or colder and which phase, which phase we started at and which phase we're headed to. The difference is whether energy is being added or removed. I just said that, endo or exo. Okay. If you are adding energy, what's that one? Endothermic. If you're taking energy away or energy is being removed, exothermic. Okay. Energy, again, is in calories or joules. We talked about that a little bit yesterday. So let's look at this graph. There are 5 regions of this graph. Okay, this is a phase change graph, meaning I have across the x-axis energy added, and on the y-axis I have temp. Okay, as I go from left to right, I'm adding more and more and more and more energy to my sample. Now, this plateaus at 0. This plateaus at 100. What's the substance? Water. Okay? This up here is your boiling point or your condensing point. This down here is your freezing point or your melting point. Again, it just depends upon the direction you're going. Okay? But let me give you an idea of what this graph is showing us. Let's say hypothetically we start at nothing but pure solid ice. Okay? And that ice is at negative 40 degrees Celsius. So it's outside currently in the state of Wisconsin. I add energy to that ice. And what happens? I warm the solid ice up. It's still solid. It has not started melting. But my ice has gone from negative 40 to negative 20 and then to 0. What happens at 0? It starts to melt. That's when the phase change starts. So at this point, after I've added, looks like 20 calories of energy per gram of ice, I have heated it up to the point where it's now beginning to undergo a phase change. It melts, it melts, it melts, it melts, it melts, it melts, until I've reached the point where it is nothing but pure liquid water. Still 0 degrees Celsius, but it's pure liquid. Then what happens? I add more energy. And when I add more energy, the temp goes up. And my water gets hotter and hotter and hotter and hotter and hotter and hotter until I hit 100 degrees Celsius. What happens at 100 degrees Celsius? It boils. We're undergoing another phase change. So, during this spot, I am pure liquid. I add energy. It's boiling. I add more energy. Boiling, 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 boiling. So right here, where now I have nothing but steam, nothing but gaseous water vapor. Okay? And at that point, if I keep adding energy, I'll heat my steam beyond 100 degrees Celsius. Okay? Steam can get way hotter than 100 degrees Celsius. Way hotter. You can actually like light a piece of paper on fire using steam if you get it hot enough. See those little twisty coils up there? That's what that's for. You see the shiny new one? I haven't tried that one yet. Yeah, we should try it sometime. Probably not right now because I don't have anything set up. Do we have time? Anyway, you can burn paper with steam. You can get steam hot enough to literally start a fire and ignite paper. That sounds kind of weird, right? That sounds strange. But again, looking at this graph, let's just analyze what's happening. Okay? Pure substance can be heated or cooled. If I have pure solid, pure liquid, or pure gas of a substance, I can change the temperature as I add heat or remove heat. During a phase change, the temperature is constant. Okay? When I have multiple phases of matter at the same time, whether I am adding energy or removing energy, the temperature is constant until I have a pure phase of matter. Okay? So during this plateau, I have solid and liquid mixed together. During this plateau, I have gas and liquid mixed together. It's only before or after those plateaus, those phase changes, that my temperature can change as I add heat. Okay? Now, a couple other things from this graph, and you've got this nice little box here with a whole bunch of explanations in it. We have the phase changes, and during those phase changes, we have something called the enthalpy of vaporization or the enthalpy of fusion. Vaporization is the fancy word for talking about the boiling / condensing point. Fusion is the fancy word for talking about the freezing or melting point. Okay. Now, this quantity, which is given the symbol of delta H with a subscript VAP, or delta H with a subscript FUS, is referencing how much energy does it take to melt or boil this substance. Now, I can give you the enthalpy of fusion or the enthalpy of vaporization one of a couple ways. I can either give it to you on a per gram basis, meaning it takes this many calories to melt 1 gram of substance. Or I can give it to you on a molar basis, meaning it takes this many calories of energy to melt a mole of that substance. Both are used, and we'll calculate both later today. Okay. So this, how much energy does it take to melt or freeze that stuff? This, how much energy does it take to boil or condense that stuff? If we are melting or boiling, we're adding energy. If we are condensing or freezing, we're removing that energy. Am I making sense? Yes, Luca.
If you could get like a pot of water hot enough, would it all just turn into steam once it reached that point, or would it slowly as you get?
Yes. Okay. So this is like your boiling pot of water. Meaning, okay, again, you're at home, you're gonna make some mac and cheese or something. Okay, you put it on the stove, turn it on. When it starts boiling, you're right here. You're not right here until you've literally boiled the entire pot of water gone. And there's nothing left in your pot. So the other problem with this graph, right, is this is a completely like sealed, isolated container. Because when you boil a pot of water at home, very clearly the steam just escapes and goes wherever the heck it wants to go. Okay. In order for this to be accurate and not for us to still have steam available to heat up hotter, we would have to have it in this controlled, sealed container. Anyway, so we can interpret this graph and get a whole bunch of data from it just by looking at the length of the plateaus and also the slope. I'll say that cautiously. The opposite of the slope, or the inverse of the slope, on the sloped areas. Okay, so the enthalpy of fusion for water is quite literally the length of that plateau. Well, the plateau starts at 20 and ends at 100. So the enthalpy of fusion is 80. Okay, now 80 what? 80 calories per gram, because that's what my graph was given to me in. It takes 80 calories for every gram of ice to melt it. The enthalpy of vaporization is the length of that top plateau. The top plateau starts at 200. My eyes aren't bugging out. And goes all the way up to 740. So it's 540 long, right? What that means is it takes 540 calories for every gram to boil water. If I would like to boil my water, pure liquid water into pure gaseous steam, I need to add 540 calories per gram. If I have 100 grams, I need to add 54,000 calories, right? You get the idea. The last thing here is the specific heat capacity. We talked about that yesterday, okay? Specific heat capacity is also specific for the phase. Ice, water, and steam all have different specific heat capacities. They're all water, they're all H2O, but solid water, liquid water, gaseous water have unique, different specific heat capacities. This graph can give us those too. To find the specific heat capacity from the graph, get the change in X divided by the change in Y. Do you remember the units of specific heat capacity from yesterday? What were they? Joules or calories divided by grams times degrees Celsius. Here is my degrees Celsius. Here is my calories per gram. If I take the change in X over a sloped area and divide it by the change in Y over a sloped area, I get the specific heat capacity. Now, careful, that's not slope, is it? In math class, it's always rise over run, change in Y over change in X. But when we're interpreting these graphs, if I want to get the specific heat capacity, I'm actually taking the run over the rise, the change in X over the change in Y. Okay. Now, how can you catch that, or how can you not screw that up? Because your brain's going to want to always just find the slope, right? That's what you're used to. How can you catch it? Keep track of the units. I want specific heat, which means I want unit of energy divided by grams times degrees Celsius. Calories per gram degrees Celsius. I want this divided by that. I want X divided by Y. So let's do that for water. Okay, where's liquid water on this graph? It's from 0 to 100. This slope. Okay, this slope is pure liquid water. Let's take the change in X over the change in Y from that spot. The change in X, that sloped area starts at 100 calories per gram and ends at 200 calories per gram. Do you agree? And the change in Y starts at 0 and goes up to 100. So my delta X, or change in X, over my change in Y is 100 divided by 100. So the specific heat capacity is the change in X divided by the change in Y. And the change in X over that sloped area is literally 200 minus 100, which is 100 calorie per gram, divided by my change in Y, which is 100 minus 0, which is 100, which is degrees Celsius. So what's my specific heat capacity of water? 1, which we already knew anyway, because that's what we talked about yesterday. Following me? Okay. So these graphs, these phase change graphs, right? I'll go back. I'm sorry. I'm going too fast. Okay, these phase change graphs can tell us a whole heck of a lot. They can give us the specific heat capacity of any one of those phases. We could also do the exact same thing we did just right here for liquid water. We could do it for solid water. We could do the exact same thing for gaseous water or pure steam and get the specific heat capacity of ice or the specific heat capacity of steam, taking the change in X over the change in Y. Not only that, these graphs also are giving us the enthalpy of vaporization, which is a fancy way of saying it takes this much energy per gram of substance to boil it. And it gives us the enthalpy of fusion, which is the fancy way of saying it takes this much energy per gram to melt it. Questions? All right. Depending upon which part of the graph you're looking at, you're going to have to use a different equation. Okay? We have two equations to help us solve for the amount of energy required to heat up a substance or to undergo a phase change. This equation on the left is what we used yesterday, Q equals mc delta T. That's the equation that's in your formula packet. We use this whenever there's a temperature change. If I tried to use Q equals mc delta T on a plateau, what would that do for me? What's the temperature change during a phase change? Literally zero. So can I use Q equals mc delta T on this plateau spot right up here? No, because I would have delta T equals zero, which means this whole thing equals zero, which means I've added zero heat. But that's not true. I have added energy. I have added heat. It's just that I need to use this other equation over here. Q equals m delta H. M is still mass. Q is still heat. The delta H is either of fusion or of vaporization. It just depends upon which one you need. Are you melting or freezing it? Sweet. Use the enthalpy of fusion. Are you boiling or condensing it? Sweet. Use the enthalpy of vaporization. You use the delta H based on which phase change you have going on. Okay? So, here are the phase changes. These are the 6 phase changes that can possibly happen. The normal 4, or what I call the normal 4, are the first 4 listed. You're very familiar with these, right? I have, whether it's endo or exo, I have an example of a reaction. The bottom 2 are the weird ones. Okay, we really won't look at those too often, because that's when we go from solid to gas or gas to solid. We'll deal with the more logical, normal ones up above. Okay, but that's there for you too. Here's another graph. What I'd like us to do is I would like us to fill out all of the information in the data table. Okay. I have over here 4 data points listed on this graph, A, B, C, and D, 4 different points. This energy added is your X value. This temperature is your Y value. So at point A, what do I have for a quantity of X? Yep, how much energy have I added? Nothing. What's my value of Y? What's my temp? Okay. Data point B, X equals, Y equals, go ahead, do the other 2. Bye, Luca.
Bye.
Have a lovely day.
Thank you so much.
Are you doing bowling and golf?
Yes, sir.
Do a simulator.
What?
Do a simulator.
Really?
You have a golf simulator? Pretty sick.
Yeah.
Who bought that?
I don't know.
I think it's for the golf.
Golf team?
Golf team, I don't know.
That would make sense, maybe.
Yeah,
It's just like a little app, there's a sensor. Swing over, but kind of sucks with money.
I would imagine. Putting sucks in real life, so there you go. Maybe it's real.
I just like thin bonds.
I wonder if I'd still slice in a cinnamon.
Oh, I had some thin bonds.
Yeah, I slice like no one's business. I'm real for it.
Me too. Or I hit straight into them.
If the ball ever goes straight when I'm like swinging hard, it's a miracle. Never happens. It's always like it's like a 90-degree angle straight right. Why I don't golf anymore. It's like the most frustrating thing in the world. Although maybe I haven't golfed in a while. Maybe I'm more calm now. Probably not. What do we have for X here for C? 180. Y. All right, cool. Now, let's fill in this, okay? What is the enthalpy of fusion from my graph? Now, let's be careful. I have calories per gram. I have degrees Celsius. I want the enthalpy of fusion. That is this plateau right here, right? What is the length of that plateau in calories per gram? 8. What is the length of the plateau for vaporization up above? Yep, should be those two lines subtract each other, right? What is the melting point? Where's the first plateau occur? What temperature does this occur at? What temperature does this occur at? Uh-huh. What is the specific heat capacity of water? How do we find that again? Change in X over change in Y. Now, spoiler alert, this is still water, okay? And we've done that already. 1. Change in X is 100, from 180, or sorry, from 80 to 180. The change in Y is 100, from 0 to 100. 100 divided by 100 is 1. We're good. Now, this is different. I have changed the units on all of these to something else. That's annoying, but that's life. Okay, in chem, depending upon the problem, you're given different units. Sometimes we get the amount of energy added on a per gram basis. It takes 80 calories per gram to melt this stuff. Other times, they'll give me a problem that says it takes this many kilojoules per mole to melt this stuff. So let's do some factor label math. Let's convert our calories per gram into kilojoules per mole. We've got to convert two things. Let's go down. Okay, I'm going to give myself some space. Do you have any space on your paper, or was I mean? I was mean?
A little bit under the draft.
Sorry, guys. Sounds like something I would do. I have 80 calories per gram. I want to eventually convert this into kilojoules per mole. I'm going to start with the calories. I'm going to convert calories into joules. How many joules are there in a calorie? There are 4.184 joules in a calorie. I don't want to stop at joules, though, right? It asks for kilojoules. Let me keep going. How many joules are in a kilojoule? Probably like 1,000. How many meters are in a kilometer? How many milliliters are in a liter? Uh-huh. How many liters are in a kiloliter? Yep. I'll just keep asking more confusing metric questions. Kilo is 1,000 of the base unit. The base unit is joules. Kilo, joule, means 1,000 of the joules. Okay? Let's keep going. I have kilojoules. Great. Now I want to get rid of my grams. What is this stuff? What's the substance? Water. How many grams are there in a mole of water? 18 point something, right? Because we have 1.008 now this year for our hydrogen. So it's going to be 18.016. And we have successfully converted from calories per gram into kilojoules per mole. Annoying? Yes, I think it is. It's kind of annoying. But depending upon the problem, you've got to be able to get from calories to joules to kilojoules, and you must understand how to get from grams to moles. You know how to do that anyway. The problem here is you just got to make sure you know which substance you're looking at, right? This is water, so we use the molar mass of water. What do I get for a enthalpy of fusion in kilojoules per mole?
6.03.
Now, this is called the molar enthalpy of fusion. Why would they call this the molar enthalpy of fusion? It's per mole. Yes, precisely. It's what you think it is. Take the 540 calories per gram and convert that into kilojoules per mole. Go for it. Same exact setup, different starting point. To go from the left-hand column to the right-hand column, all we are doing is converting stuff. I am having you practice conversions because sometimes problems give you labels that they don't want in the end. Here's a value in calories, solve for it in joules. Here's a value in grams, solve for it in moles. Here's a combined value in calories per gram degree Celsius, converted into kilojoules per mole times Kelvin. All of these conversions are pretty easy on their own, but when you combine them, it's a little tricky sometimes. You might flip-flop something or screw something up, but you should be able to convert this stuff. What do we get for the molar enthalpy of vaporization? Converting the 540 calories per gram into kilojoules per mole.
40.70.
40.7? Yeah? I trust you. How do we go from Celsius to Kelvin? Add like 273. That's it. If you don't know, it's in your packet. Under the gases, liquids, and solutions section, midway down, K equals degrees Celsius plus 273. That's all we do. Whatever the Celsius temp is, you add 273 to it. So if it's 0 Celsius, it's 273 Kelvin. If it's 100 Celsius, it's 373 Kelvin. That's easy. I'm not going to make you write that one out. Specific heat capacity. Change your 1 calorie per gram degree Celsius into kilojoules per mole Kelvin. If you need to write it out, write it out. If you feel confident doing this in your calculator, do it that way. But you got to be able to get it right. I don't care which method you use. I don't need to see this conversion per se. But you got to be able to obviously do it. That's the hard part, I guess. How's that Celsius Kelvin treating you? Anyone confident? I'll take that as a maybe. You know how to convert calories to kilojoules, yes? You know how to convert grams into moles, yes? Now, when it's per Celsius or per Kelvin, what do I have to do? I'm assuming maybe that's where you're hung up. Because again, you know how to do the other ones, right? We know how to get from calories to joules to kilojoules. That's this. Grams to moles, that's that. How do I switch my denominator from degrees Celsius to Kelvin? What do I need to do? Have I confused you? But you're adding 273, yeah. Okay, so let me stop confusing you. The difference of 1 degree Celsius and the difference of 1 Kelvin is the exact same. Yes? Meaning, if I go from 0 to 100 Celsius, it's the exact same as going from 273 to 373 Kelvin. It's a difference of 100. So if I am changing the calories per degree Celsius or per Kelvin, is there any difference? There's literally none. It sounds really weird. But in order to increase the temperature by 1 degree Celsius, it takes the same amount of energy to increase the temperature by 1 Kelvin. In other words, whether the denominator is per degree Celsius or per Kelvin, it doesn't change the math or the value. It does not change the math or the value. So I could write this as calories per gram Kelvin. It's still 1. I could write this as kilojoules per mole degree Celsius. It's still whatever that would be. Okay. Did you convert it from calories to kilojoules and grams per mole? Did you do that part at least? What'd you get? Seven, 5, 4, if I'm not mistaken. Okay. You didn't know you were getting a bunch of conversions today. Sorry, guys. Okay, 0.0754 kilojoules per mole Kelvin. Again, when it's in the denominator, whether it is degrees Celsius or Kelvin, it's the exact same. It takes the same amount of energy to raise 1 degree Celsius as it does to raise 1 Kelvin, because the difference in Celsius and the difference in Kelvin is equivalent. Okay. All right. Of solid, liquid, and gas, write the phase or phases that are present between A and B, between B and C, and between C and D. What phases of matter exist on this plateau, during this plateau? Solid. What's happening during this plateau? It's melting, so what else is there? Liquid. During that flat spot right there, we have solid and liquid. What happens when I hit this point? It's pure liquid. nothing but liquid on that incline. What happens when I hit this spot? That's where it starts boiling, right? This is boiling occurs right here. It starts right there. So during this plateau, what phases of matter do I have? Liquid and gas. And if I kept going, what would this be right there at that last point before it goes increasing again? Pure gas. Pure gas. Okay. Well, yeah, it does really weird things at high temperatures. There's like, I mean, there's plasmas obviously as well, but like once you get to extremely high temperatures, like phases of matter are kind of almost irrelevant. As weird as that sounds, it's hard to classify and quantify what phase it's in. Anyway, identify the phase changes. Identify whether they're endo or exo. Go for it. I'll stop yapping at you here for a little bit. See if you can identify what phase change is happening. See if you can identify whether the three processes on number 2 are endo or exo. Go for it. What phase change is this? What's the phase change? Boiling or vaporization? What's the phase change? Uh-huh. What's the phase change? Endo or exo? I am melting something, right? How do you melt something? Do I put energy in to melt it, or do I take energy away to melt it? Put it in. You're right. Endo. Freezing. Do I put energy in to freeze something, or do I take energy away to freeze something? Take it away. Exo. Boiling. Do I put energy in to boil it, or do I take energy away to boil it? Yes. Endo. Okay. Those get a little tricky. And this is what I was talking about in my video from last week, Thursday, at the end of it. It's not always easy to identify endo or exo. It can be a little confusing because of different scenarios that kind of present themselves. What I mean by that is in the laboratory, okay, or even like, I guess in your normal life, right? If you're burning something, okay, whenever you burn something, it is exothermic. It's releasing that energy. Hence why there's fire and you feel the hot, heat, right? The hard part is that when we boil water on the stove, it's hot. Now, why is it hot? Because of the stove, right? The process of boiling the water, the water boiling in and of itself isn't releasing the heat, right? It's that hot stove that's adding the energy to the water that's providing, extra heat for us too. So it's confusing. You got to make sure you understand whether is energy going in or is energy coming out. If energy's going in, it's endo. If energy's coming out, it's exit. Use the molar enthalpy of fusion. Using the molar enthalpy of fusion. Actually, I don't want the molar enthalpy. I lied. Using the enthalpy of fusion. Sorry about that. How much energy in kilojoules is removed to freeze 64 grams of water? We're going from here to here, from B to A on this graph. Pure liquid to pure solid. How much energy does it take to freeze 64 grams of liquid water? Now, we have an equation for this. Okay, we have two equations that deal with this graph. They are Q equals MC delta T and Q equals M delta H. If there's not a temperature change, which there isn't, we cannot use Q equals MC delta T. We're going to use Q equals M delta H. Okay. What's the mass of the water? Okay. What is the molar enthalpy of fusion for water? Sorry, did I say molar? I don't want molar. I apologize. I told you to cross it off, and then I still keep trying to use it. Yes, I want the calories one, because that one's per gram, right? Why do I want to use this? Because it's per gram. And what was I given my quantity in? Grams. So let me use what makes sense, right? I want these labels to match. So I have 80 calories per gram. The grams will cancel, and I'm left with just calories. Is that what I wanted in at the end? No, I want it in kilojoules, but I can convert that after the fact, right? So 64 times 80, how many calories does it take? Or sorry, how many calories are removed to freeze this?
5,120.
5,120 calories are removed. How many kilojoules is that?
21,420.
Are you sure? Kilojoules?
On. Oh, no, man. I didn't see it.
How many kilojoules was released? Is there another way to do this problem? Yes, there is. What I did is I took my grams and the enthalpy of fusion in calories per gram to get the calories first and then convert to kilojoules second. I could have switched my grams of water into moles of water and then multiplied by my moles of water by the kilojoules per mole to get the kilojoules. That would also work. Same answer, different process. Okay, totally up to you whether you want to convert on the front side of this problem and change this into moles right away and use the other value, or keep it in grams, use the value per gram to get the calories, and then convert the calories after the fact to get the kilojoules. Either way is fine. You'll get the same answer. Whether you prefer to convert on the front side or the back side is totally up to you. But there's more than one way to do this problem. Try this one. We'll end here. I'm sorry, we don't have enough time. Just kidding. We'll pick this up here tomorrow. People at home, have a lovely day. Thank you for joining me. Homework topic 1 is due tomorrow night. People in front of my face, grab a wipe.